Thank you very much. So my name is Denise Risch. I work at the Scottish Association for Marine Science in passive acoustic monitoring of marine mammals mostly. And what I wanted to do in this talk today is just to give a broad overview about the passive acoustic long-term projects that we have ongoing and we're collaborating on with other partners in Scotland and wider afield, and the challenges that are a result of these long-term data sets, and how AI and deep learning, machine learning methods are helping us to overcome them. So just as a bit of an introduction, we work primarily on the west coast of Scotland. Since 2017, we've been running several long-term data collection efforts with various partners, Marine Scotland, SAM CHI, as well as AFBI in Northern Ireland, and others who have been collaborating on this network. The different dots on the map that you see here are different long-term projects that lasted from about a year to longer, up to 5 years. We're typically collecting data using moorings that are retrieved by an acoustic release mechanism, and we collect broadband acoustic data as well as data that is being processed in the field already, depending on which species we are interested in. And what, the interest there is to collect data on different marine mammal species and get a understanding of their distribution and seasonal habitat use. And as you can imagine, these long-term data produce a lot of data volume. So one project that we've been working on between 2017 and 2022 was the Compass project. So if I go back to the map, those are the yellow dots here on the map. So the moorings were distributed between the top of Lewis and the Outer Hebrides and down to the Northern Irish coast. And for this project alone, we had over 100 gigabytes of click detector data and over 120 terabytes of broadband acoustic data. So that's a lot to analyze, and we've just been scratching the surface so far and really digging into these different data sets. A lot of the work, as I mentioned, we are interested in is to look at the distribution of different species of baleen whales, for example. So if we look further offshore on the outside of the Outer Hebrides, we had one acoustic array deployed with funding from Marine Directorate. We called it the Samosas array, and we were trying to learn more distribution of large whales such as fin whales, humpback whales, or minke whales and sei whales, which occur in our waters, but we know very little about because we just have a lack of data in terms of visual surveys from these more offshore areas. And so what you see here is 1 year of data analyzed and in terms of hours with detections per week for these different species, and it shows you the different seasonal patterns for these different species. And we've mostly analyzed these so far manually, which takes quite some time, but that is because there was so far an absence of robust species-specific classifiers for all of these species. Similarly, we looked into the presence of delphinids. We've got 5 to 6 species in these waters, and at the moment there is a lack of species-specific classifiers that can robustly identify different species, whether it's the bottlenose dolphins or rhesus dolphins and others in our data sets. So what we've done in the absence of species-specific classifiers, we've run generic click and whistle detectors and looked at the distribution of presence of delphinids as a group in this data set so far. So there's obviously a lot more that can be done with these species, but we need better automated tools in order to to allow us to go through this big data volume. We collect a lot of our data using static passive acoustic recorders, but there's also other techniques. You can collect acoustic data using towed arrays from vessels. More and more, we are also using ocean gliders to where we add acoustic recorders on the back of them to reach these more offshore waters that have generally a lack of data, as I mentioned. The advantage here as well is the combination of collecting oceanographic data and habitat variables together with the acoustic data and presence of animals. So for these applications as well, we need automated methods in order to detect different species so that the data, we can fully analyze the data. Our colleagues at NOAA in the US, they have started to put a lot of their detection data. They are using very similar methods to us. NOAA has created this acoustic cetacean map, which is on the web a couple of years ago, where they allow the user to dive into the data that they are holding, subsetted by different time periods and location and species to find out which species is detected when and where and with what persistency. And at the moment, we lack similar data portals in the EU or in the UK. We do have the JCDP, so the Joint Cetacean Data Base, which currently holds primarily visual data. And what we are aiming towards is to add passive acoustic detection data to this. But this requires a good data sharing tools and platforms, as well as the ability to analyze this data. And so I just wanted to show and highlight some of the projects that we've started working on over the last few years for different species, and that's all ongoing work that several PhD students here at SAMS and wider in the wider Scottish community have been working on. So one species we were interested in were humpback whales, which are seen more frequently in Scottish waters in recent years, or reported more frequently, and they are also singing in our waters. Humpback whales are interesting in that they, during the breeding season and also on migration, they produce these quite complex patterned songs that pose an additional challenge to automated detection because they change over time. So every couple of years, the songs might, and the notes in the song, of which you can see a spectrogram here. So for those who are not familiar with spectrograms, so you see time against frequency and the loudness of the sound on the color scale. So these sounds are complex. They change over time. So any system that is trying to detect them will need to be adjusted accordingly. And colleagues at and together with Google a few years ago, built a deep learning model for humpback whale song for the Pacific, using a very long-term, over 10-year data set from a lot of different recording locations, as you can see on the map here. They got relatively good precision and accuracy results with their approach, and they opened the code, and we started by trying to use their model and apply it to the North Atlantic humpback whale song, but found that the precision and accuracy went down in applying from one ocean basin to the other, which is not a surprise, because the song will be different, even though it is some of the notes might be similar. So the way humpback whale song is structured is that you have different themes that with recurrent phrases and recurrent units. So you have to make the decision of at what level you're analyzing the sound. Which we have done. So we use this model and try to apply to the North Atlantic, and realize that we'll probably retrain it because it wasn't generalizable to this new site. And our PhD student Vincent Carter used data from Scotland, Iceland, the US East Coast, and the Caribbean in order to try and develop a model that could be used across the North Atlantic. So he based this analysis on the Allen model, and then but retrained it with North Atlantic data. He applied several augmentation methods to and denoising methods, and looked at training the model on the unit level as well as hourly and daily detection levels, because that's usually, if you look at long-term data and in a monitoring and regulatory context, we often just don't need the granularity of detecting every unit of a song, but in some application that might be useful. So he developed a convolutional neural network architecture that is also can also be retrained for other species. Here's the precision recall curve. The red line is the overall curve. So based on using different thresholds, we get quite a high recall and precision, which we were quite happy with. The outputs of the detector are shown on the right here. So we can either look at it in terms of hourly presence and absence of the species, or we can, if you're interested in the number of calls or units, we can also look at that. So we reached an average precision of 96% on the unit level. And yeah, building these detectors is useful, but in order to really make them usable to the community and in different contexts, we really need a framework that can be used to share data and to share the tools across different researchers, so that if we are analyzing data sets, the results are comparable. And so the one of the analysis software that a lot of us in the bioacoustic community, or in the marine bioacoustic community in particular, are using is called by colleagues over in St. Andrews, and they have integrated a deep learning module into this software package, which allows to upload new deep learning modules that are being developed for different species. And so that's what we have done with the humpback whale model as well, which is available in this software package, so that other groups can use it and also retrain it if necessary. And the code is also published on GitHub, and the paper just came out a few months ago. In Scotland, we are interested in detecting a range of species, as I said, using our acoustic methods, marine protected areas and monitoring for key species such as rhesus dolphins or minke whales and harbor porpoises, for which we have existing marine protected areas, is particularly key also for the regulators. So we've been focusing on these species to develop new detectors as well. So we looked at minke songs, another baleen species, low frequency sounds. Here's an example of one of their sounds. They're typically less variable than humpback whale song, and they also don't change as much over time. So they're in some ways an easier signal to detect. But being so low in frequency, they also often overlap with vessel traffic. So there's also that challenge of detecting signals and noise, which is inherent in all passive acoustic data, but probably more of a problem for these lower frequency species. Again, here we used a similar approach and similar group of collaborators. So we collaborated with NOAA on the US side of the North Atlantic, who hold a very large passive acoustic data set, and we added recordings from the west of Scotland of those arrays that I showed you earlier, as well as from the east of Scotland data that were provided by the Aberdeen Lighthouse station. And we again used CNN to try and detect these sounds, and this was developed in the KETOS framework for building these models. And again, trying to make this detector available for the wider community to work on it collaboratively. So yeah, this just shows you the data pipeline, the training and testing data sets. We had about 18,000 annotations that we collectively had been annotating manually in our various data sets, and then trained the model using Cathos. In Python, the outputs is selection tables and another software program called Raven, which can be used for post-processing of detections, and the final output will also go into PAMGAD, so that the detector can be used in various contexts. So here are some first results that we've got from this effort. We're currently preparing a manuscript. We're still working on some issues. So the performances are generally a bit less than the one that we saw for the humpback whale detector. On a daily present, we are 90% precision and 98 for recall. But if we want to call to count individual calls, we are much lower. So there's and we also have discovered recently that depending on recording sites, we have quite a difference in terms of false positive rates. So we're still working on this. At the moment, we are annotating more data in order to retrain the model, and hoping to have this published by the summer and then integrated in PAMGAD as well. And yes, I said various dolphin species. We have a suite of species that we regularly see in Scottish waters, and One of them is the rhesus dolphins, a protected species for which we have an MPA north of Lewis, and our PhD student Thomas Weber is currently working on their clicks to show these spectral bands that you can see on the left here, which are useful to for classifying these clicks, and he's working on machine learning models in order to automatically analyze the recordings that we have from this site. Similarly, different approach. Klein, a PhD student at St. Andrews University, is at the moment looking at building a generalizable acoustic classifier set for all the different Northeast Atlantic delphinid species, combining clicks and whistles. So he is taking the approach of building individual CNNs for these different types of signals that these species produce, and is combining them then to look at the encounter level to make predictions of species presence. So instead of looking at an individual species, he's taking the approach of building a classifier that can identify several species, which will also be soon be openly available in PAMGAD. And then there's lots of other different sounds and species like fish that are vocalizing, as well as environmental. So she broadly looked at the finite whistles, click, vessel noise, and general ambient noise to get an overall view of the soundscape, which then can be looked at in more detail in a second step. So various applications of AI to look at these long-term acoustic data sets, of which we have terabytes and terabytes in our different institutions. So and just to conclude, we do have lots of data available from various sites around Scotland and the UK. We generally lack annotated data, and that's what we're working on at the moment. And I think that there could be a lot done in terms of sharing and collaborating, and also developing efficient tools for doing these annotations. The detectors and classifiers are developing rapidly, but they need to be robust across very different recording contexts and location, different signal to noise ratios, recorder setups. We all use slightly different methods. Towed versus static acoustic data can be quite different. The different species might show different behaviors at different times of years. So all of these things need to be taken into account and require a lot of retraining and testing that offers the possibility for collaboration across different institutions that hold these types of data. And that's all from me. I'm happy to answer any questions. Thank you.
Sorry, I'll turn my camera on as well. Hi, that was really interesting thing. I was just wondering, maybe I'm not that super familiar with the exact nature of PEM and that concept. Was I right in understanding that you extract spectrograms from the sound files, and then that's what you use for the AI driven analysis?
Yeah.
In which case,
typically, some people have worked, and for the click detection, we are also using the waveform of the click but yeah, most approaches to the humpback whales, minke whales that I've shown, and also the soundscape analysis, that was all done on spectrograms. So that's image analysis in essence.
Okay.
Yeah.
I guess my question was, does that create sort of, I don't know, a compression artifact or something like that, depending on the range of wavelengths versus what you can put into the image? Are there any limitations, or do you introduce any kind of artifacts through that route?
Not quite sure what you mean by artifact, but
I guess, I mean, like you have a set number of frequencies, and or you have a wide range of frequencies because you're also using broadband, right? And I'm just wondering to what extent the generation of image information clips or distorts or bins the acoustic information in a way that has an impact on analysis.
I mean, I mean, resolution of the spectrum plays a role, and you need to be aware of of your sample rate and whether you're decimating the data. But if you're interested in the low frequency spectrum, we can obviously use a different decimation, and also in order to, and that's sometimes done directly within the tool. For the humpback whales, we basically have a pre-step that basically normalizes the data so that it's all at 10 kilohertz, and then there's various preconditioning and denoising that is run before the detection process. So I suppose it's important to know what your sample rate in the field was, and that needs to be high enough to so double the highest frequency in your signal, and in order to not create this distortion, and that's being done in the recording. Yeah.
Okay, thanks. Huge amount of work in its own just to get to that stage, I guess. Thanks.
Between dolphin species acoustically in the near future?
Oh, yeah, for sure. So Tristan Klein at St. Andrews has made really big progress on that front, and he's going to present his results in June, I think, at the Detection Classification conference in Rotterdam. So yeah, it will be possible, but there will be a lot of testing being necessary in different locations and contexts. But yeah, I think that's in reach, hopefully.
Thank you very much. Another question also in the chat from Tom Morgan. I believe I'm correct in that you have been using convolutional neural networks to analyze the data. Have you utilized recurrent CNNs in order to exploit the temporal nature of the data to possibly improve predictions?
Yeah, I don't know the details of it, but I'm fairly certain that Thomas Weber, who has been working on rhesus dolphins and focused on the clicks of the dolphins rather than the whistles, because that species in particular is known to whistle less than that they click, and he's used recurrent CNNs, but you'd have to get in touch with him for more details. You're muted.
Thanks for the interesting presentation and the work. So I just want to understand about certain things. So for Pacific and North Atlantic, I understand due to the nature of the location, the songs of the whales vary quite frequently, right? So do you have any study or report kind of what sort of degrees of varying over there? Because if we want to understand, for example, the minke whale from Pacific and minke whale from North Atlantic, how the nodes changes over time, or what degrees of that. That's my first question. And if it is there, so on your first case study, you have mentioned like for the Pacific data, the accuracy was 97%, but North Atlantic data is 79%, right? If I'm correct. So did you retrain the model from scratch from the North Atlantic data, or you just used kind of pre-trained model over there, the weight utilized over there? So I assume if you use the weights from the Pacific data, the accuracy might bump. That's my feeling, and that's one thing. And yeah, that two question is from my end. And also another thing I want to add on top of that, you are like adding kind of image-based analysis of bandwidth kind of image way, right? Why analyzing from image perspective? Rather, we can always go back to the spectrogram of the signal and then analyze based on that the data and the classification, rather treating it as an image. So thank you.
Yeah. So in answer to the first question, that really depends on the species, what we know and what we don't know. For humpback whales, we know quite a lot because they're species that have been traditionally gotten more attention from research. So we know their songs in the Pacific quite well, and also those from the North Atlantic. They've been recorded since the 60s. We do know that certain nodes and those vocalizations are similar across ocean basins, and therefore we could use the pre-trained model from the Pacific. That's why we started with that and applied it to the North Atlantic data to see how well it would perform, and then we retrained it because the song. So I showed the pattern of the song. It shows different patterns that vary over time. The frequency content is similar though, and the frequency range, but the notes can look quite different over time and over space. So there's a lot of species where we are missing the full vocal repertoire. Some species have not been described at all, and let alone the geographic variation in their signals. So a lot of species we know well from one side, but not the others. So that global development of detectors can be difficult, and also in many species is not useful because there's quite a lot of geographic variation. So that would be the case in minke whales, for example. The Pacific animals sound very different from those in the North Atlantic, so you'd have to use different approaches. In terms of the humpback whales, I believe we used the pre-trained model and then trained it with North Atlantic data. That's the way we went about it. And sorry, I forgot your last question.
Yeah, so the last one was while training the model, you mentioned about the annotation. So I believe it's kind of a spectrogram and taking the annotation and treating as an image form for the training. So why treating the data as an image form? Rather, we can directly treat the spectrogram as an input to the model, rather treating as an image, because have some kind of artifacts which Jens already mentioned. I think it's worth worth a try without the image annotation, rather directly pass the signals.
Okay. Yeah. I guess we do use the spectrograms for identifying the sounds and creating the annotated data sets, and yeah.
Okay, thank you.
Right.
Denise, I would have a question as well. You mentioned that some of the code is available online on GitHub. I'm wondering, is the raw data also available online? So if somebody that is, let's say, passionate about AI, deep learning, could they have a go at testing and playing with the method and with the data?
Yeah, I need to check. I'm pretty sure that for the Humpback data, we've also uploaded the training and test data sets that was used. There's also other acoustic repositories online. A lot of the data that has been collected in US waters as can be found online. As I said, where there's limitations at the moment is at having annotated data sets. So there's a small set, but that is definitely something that for many species we are actively working on. And obviously that as manual analysis and takes a lot of time, and where I'm hoping that in the future we find ways to better collaborate between institutions to be faster at that, and also to build tools together that, because some of these models could obviously help with annotating as well. If you have a pre-step of pulling out signals and then use that for annotation, that is being done project by project at the moment. But I think where we could be better is by working together and sharing those annotations and working together to create bigger data sets that are then shared online, as you say.
Thank you. Tom?
Hi, Denise. Thanks very much. Very interesting. You mentioned earlier in the talk that you were collecting sort of physical parameter data through gliders like chlorophyll and temperature. Are you sort of fusing that with in a sense, the acoustic or the image analysis in any sense of trying to understand and relate the environmental characteristics with the acoustic characteristics?
I mean, that's we are in the early beginnings of using gliders with PAM. Again, the Americans and the Norwegians are a little bit further along there. In the UK, we've missed the or had a lack of the tools for a while, but so the idea is to look at the detections of different species and relate them to the environmental variables that are collected at the same time, to then learn about the preferred habitat of that. That's what you mean.
Yeah, and I was just wondering whether you could bring in other types of data and to predict. I mean, if a machine could learn that a particular type of whale was often at a frontal system, whether you could actually use it to help inform the model that noise it was looking at was actually this type of whale, that sort of thing, really.
Yeah, definitely. So that's being done with spatial distribution models, and the glider data could be very helpful in just accessing these offshore habitats and collecting both the species presence as well as the environmental data there that can then be linked in various models for predicting habitat preference. That's quite standard, and it's being done with visual as well as acoustic detection data already. Yeah. Yeah, I'm just seeing in the chat that Luis put the GLABS, the Global Library of Underwater Sounds, in the chat there. That's a good resource, a good effort that has begun a few years ago of trying to build a large group of people from across the world collecting passive acoustic data, have put a library of underwater sounds together. That's still in development. I don't know, Luis, whether you know more about the project and where it's at, if you want to say some more about it.
I just know that it's kind of a call to share tagged sound data to try and get towards what you were saying about, you know, for training models, you would want to have the sounds of the same species from that occur in different places around the world, and having that information would improve model training. So it's kind of a call to get everyone working in the field on board with that.
Thank you.